Namaskar and welcome to episode number 22 of Understanding Consciousness podcast. Bayesian brain, the Bayesian brain. We are talking about the Bayesian brain today, and the idea of brain being a scientist is what we are going to look into deeply. What do you mean by Bayesian brain? Well, Bayes theorem in probability is an interesting um, idea to figure out better, more easily, and deeply, more accurately the the predictions of the world based on new data. Okay, what am I talking about? Um, have you guys heard of the Monty Hall problem? The Monty Hall problem is this game show that has three doors, and the game show host tells you that one of those doors has a car, the other two doors have goats. Of course, you being the 21st century contestant doesn't have to, in the first world, doesn't have to, doesn't want to manage goats. You would rather have a car. You choose a door, one of the doors, and hope that you get a car instead of a goat. What happens is, then Monty, the guy who is the host, opens one of the doors that contains the goat, and then asks you whether you want to change your choice from the door you chose to the other unopened door, or do you want to stay where you are? What would you do in such a case? And if you go look into this problem, you realize that people actually think that it shouldn't matter. Now one of the doors is open, which has a goat. The other two doors that are closed um, have equal probability of one having a car and the other. How does that even matter whether I change or not? Is the probability of winning not 50% for both? That's not true. That's not true at all. It is actually twice as good, twice as likely that you'll win if you change your choice. No matter what you chose initially, in this second step, when you have a choice to change it, you should always change it. Why does that? Like, how is that true? Well, um, this is where Bayes' theorem tells you. And if you actually do this experiment hundreds and thousands of times, you'll realize that you'll win 66% of the time if you switch, and you will lose if you do not switch. If you need an intuitive way to understand it, think of this problem in this way, where you change the number of doors from 3 to 100, let's say, or 1,000. Let's go to 1,000. You have 1,000 doors in front of you. He tells you to choose one of them. You choose one of them, and then what he does is opens 998 doors containing goats, and one door which you have is never opened, of course, and there is one more door left where you can switch to you can either switch or stay. In this case, my intuition at least says I would definitely switch, because, well, what are the chances that my door contains the car? Is 1 out of 1,000, right? 1 out of 1,000. But the other door, it's because Monty is not opening doors by himself just randomly. He's not opening doors randomly. He knows where the car is. So he's not going to open the car door and going to open all the goat doors. So there's a high probability that the other door is the car door. Is it intuitive? It's very intuitive to me all of a sudden, but I can understand if it's still not intuitive. But what it tells you is interesting. just look into it. If you don't understand, just go into look. I don't want to get into it because I want to go forward to how it applies to the brain. Well, what happened here was you made a prediction initially, right? And then new data came out. Okay, new data came out that that was related to what you chose. So that new data should change some prediction that you have, right? And that is what the Bayesian brain is all about. You make a prediction, you get more data, and then you change your prediction based on new data. That's it. It's simple, but it is deep. It has very deep implications in the sense of now um, now you realize that if your initial prediction was bad, the new data is going to make it better. But had you chosen a better one initially, a better prediction, the new data would have helped you even more. Maybe that's the you can think of it that way, that initial predictions also matter. Data also matters, but initial prior, these are called a priori or prior, the priors, Bayesian priors. And what happens afterwards, what you come up with, what predictions you come up with after you get the data, is called posterior, Bayesian posteriors. Okay, whenever you read prior, think of it as before, a pre-judgment of the situation that you are in. Again, how is it now related to the research that we are focusing on? It's very interesting. The research that we are focusing on, this paper, which is called Perceptual Awareness and Active Inference. Active inference, the active part of this inference is what we are interested in here. The paper, as explained yesterday, the paper talked about how the way in which a scientific brain as a scientist would perform experiments, it should consider data as to be really important, right? Then why does it happen that in Troxler fading that we saw yesterday with the cat, um, why does the why do we have these experiments and these situations, these phenomena where perception changes even when the input call the perception changes even when the sensory input hasn't changed. Even when you are focusing at the center, your eyes are focused on the central dot, slowly the colors fade. The colors fade, which means the perception changes. Now, why is that? Why should it happen? And it will become clear with this idea that you Bayesian the Bayesian idea that we have come across, that we have explained, tells you that priors are important. So it's like what are priors? Priors are hypotheses, and then you get data, and then you change your hypotheses. Right? The the initial, the starting hypotheses that you use is important as well, and you should be checking different hypotheses, right? This is the reason action is a part of this whole situation, or so as the paper postulates, or the paper tells. This research paper talks about that this can be explained, this phenomenon where the the sensory input hasn't changed, but the perception has changed, can be explained by understanding that action, in this case the movement of the eye, in Troxler fading, the movement of the eye is an integral part of the experimentation. It's to try to vary your initial condition as to have a different prior, a different, does it make sense? um, I'm not very comfortable with this yet, but I think this paper will make me extremely comfortable, not extremely, but more comfortable with this idea. One more um, thing that we discussed yesterday was, one more phenomena is the binocular rivalry. When two eyes are looking at different objects, what the perception would be of the brain switching between the two percepts randomly. First, you'll be focusing on the left eye's perception and then the right eye's perception. And in this case, also the same thing is happening. The the sensory input hasn't changed, but the perception changes. What is the action that is happening in this case? It's not eye movement, it's the attention movement. The movement of attention between the two different percepts. So attention itself is an action, of in this theory, in this hypothesis. Action itself is something that has to be a part of. Attention is a part of action for that to make sense, and action is a part of trying to get better data, more varied data. And I think one more reason is that the minds our minds are not looking at a static world. The world is ever changing. Because the world is ever changing, the idea is that you should be getting data, you should be discarding older data because the world might have changed by now. And I think that's why action is also important in understanding inference. So this is where I stop. Tomorrow we'll go through the actual active inference topic in this paper, and we'll go through some science. A lot of mathematics, I think, is in front of us, but don't be scared. I am here. I'll do the scary part, and hopefully we'll get something out of it. The active inference model is getting more clear in our minds, how the brain is a scientist in two ways. And whenever you try to think of an example of this, don't think of it from your own life, from the way you consciously do things, because we are not scientists. We do a lot of intuitive work, but think of the fact that how your intuition is formed. Think of the example that how language is understood, how we learn how to walk, how we learn how to do anything. That part of the brain, that part of the unconscious processes that underlie all the intuitive understanding, is something that is done through the scientific process. So even when our conscious minds are not very scientific, our brain actually is. So that's what I think I understood from it, which is very exciting, because we can leave a lot of things to the unconscious mind. We can believe in that part of our brain more, in some ways, because we can believe in the learning ability of our unconscious mind, which is, I think, very important in our lives as well as a pursuit to understand the mind. So see you tomorrow with more information on Troxler fading. Nice word, no? See you tomorrow.